Hi guys, today I want to share with you this modern perspective on derivative. Um, Many of us struggle with understanding the meaning of a derivative, so I want to clear those things today. Why should you bother to watch this? If you cannot answer these questions, I would recommend that you watch this video till the end very carefully and take notes because some of the points are very important. So if someone asks you what is a derivative, um, most of most likely you will say the slope of a function. So but if it is the slope of a function, why not call it a slope? Yeah, why do we call it a derivative? Why do we need a new name if it is just the slope of a function? So something must be wrong with this simplistic view. And is there a way to understand differentiation without limits? Yeah, because limits is something which hides many things under the mathematical rug, and it would be nice to um, just focus on the concept of the derivative without being lost into the details, because limits is too much detail. We want the punchline. And you must have heard differential. If you are asked to define a differential, most likely you will say a small quantity, but how small? Yeah. If you cannot specify how small, then you have a problem. And when do I need limits? If I can explain these things without limits, which I will try today, when do I need limits? So let's begin. So the focus of this video will be the geometric view rather than the limits view. So I will start with a very humble polynomial, a quadratic polynomial. You can choose these coefficients to be anything you like. And we must distinguish. So this x typically is the independent variable. And when you have a function such as this polynomial, and if you plot this, you get a graph. So on the y-axis, we have the dependent variable, so y depends on x, and the relationship between these two is a function p. So p is the function. So don't confuse this p with this y, because this is the variable and this is the function. Now if you plot this may look something like that depending on these coefficients. So say I choose a point, yeah, let's say that point is r, and I want to know how this function behaves at that point. Now I'm very familiar with linear functions. Yeah. Why? Because a linear function, unlike such a function, they have a very simple graph. The graph looks like that. Now at any point, yeah, or between any 2 points, a linear function will be represented actually in this plane by a line. And the beauty of a line is that it has just two properties, a slope, yeah, and an intercept, yeah, at what point it intercepts the y-axis. Now the slope is defined only for a line. Let me make it very clear. There is no such thing as the slope of a curve. Yeah? There is only the slope of a line. And that is why we are doing this business. So if slope was easy to define for a curve, then we would not need this name derivative or this complicated concept. So which means that I have a curve, in this case representing a quadratic polynomial, and I'm looking for a simpler function which has just two properties, yeah, the slope and the y-intercept, and I want to see how can I connect these two functions. Yeah, the simpler one which has just two properties, and the complicated one. So I want, because I want my analysis to be at this point, yeah, so I want this function, this linear function, to capture two aspects of my polynomial. Yeah, it can only capture two aspects. Yeah, because it has just two parameters or two coefficients. So the graph of this linear function, which will be a line, it must intersect the graph of the polynomial, yeah, at that point. Yeah. So I must have, for example, if this is the point I'm talking about, at this point the line must be, so for example, if this is the line, it must pass this point. Yeah. Of course there will be many lines, yeah, and so on. So, but this is the first condition. That's not the only condition, because just intersecting the curve at a point is not enough. So there is one aspect of it. The second aspect is that the line should be oriented in such a way that it represents the true direction of the curve at that point. So you see, there are many lines and not all of them are representing how the curve itself varies near R. So how do we find that? For that I will start with this linear. Actually I will represent both this linear function and the given polynomial. I want to express them. They are given as functions of x, yeah, but I want to write them in terms of the difference, yeah, because I want to know what happens at x is equal to r. So yeah, x minus r will tell me how far I am from r. Yeah. So this will be x minus r. If this is r, this will be x minus r. So I can use a trick. Remember, L is b naught plus b1x. Yeah, the original L is b naught plus b1 x. I can replace this x with this quantity. Yeah? So r plus x minus r. Add r, subtract r, you still have that x. The advantage I have is that I can write this in terms of x minus r, you see. So b naught plus b1r is separated as a constant, and b1 now multiplies that difference, deviation from r. I do the same trick with the given quadratic polynomial. I replace x with r plus x minus r and do some algebra, and here I isolated a constant which is the same as polynomial evaluated at r. Then I have a coefficient multiplying x minus r, just like we did there. So you see, so far the form is the same. I have a constant here and then I have a constant there. I have some constant multiplying x minus r there and the linear function, some coefficient multiplying x minus r there. Here is the difference. This given polynomial also has a square term, x minus r square, and this was expected because this was the quadratic. That was not quadratic, so we did not have it there. So we want to know, because we want to use, we are searching for a linear function which is capturing two aspects of our polynomial function, and to see how good that representation is, let's investigate the difference between these two. So we would like to investigate how different these two are. Yeah. Of course, these two must not have any difference at x is equal to r. So if I replace this with r, so the polynomial at the chosen point and the linear function at the chosen point, they must not have any difference. That's the first requirement, that's the first aspect. So which means that L of R must equals P of R. Yeah, that's the requirement. That simply means that what was L of X? If you remember, L of X was B0 plus B1X. Now I want L of R, which is B0 plus B1R, just set X to R, and I want this to be P of R. So which means that let me do some trick here. L of X must be B0 plus, actually I already I should have used that function. I should have used that form to simplify my life, because I don't want to lose that trick. You see, this was the trick. I expressed L of X in terms of X minus R. So if I go with that, I have B0 plus B1R, the constant, plus B1 times X minus R. Yeah. Now I want this, if I set X to R, I want this side to be equal to P of R, you see, because I don't want any difference. So and remember, setting X to R will turn this to 0, which means that these two must be the same. Yeah? So this part, the constant part of L, X not including X minus R, must equal P of R. That's exactly what I have done there. Yeah? That doesn't change. B1 times X minus 2R doesn't change. But the constant part, which is B0 plus B1R, it must be equal to P of R. And you can, even if you don't follow this reasoning, you can check it there. Yeah? If you want to know why this must be P of R, yeah, and nothing else, just set X to R. So L of R will be P of R, because that will be 0. This is a requirement. Yeah? This is the requirement. So now we can remember this difference was required to be 0 at X is equal to R, but I want to analyze this difference in the vicinity of R. Yeah? Not just at X is equal to R, but near X is equal to R, which means that we need to examine this quadratic difference, the difference between the given function, which is a polynomial in this case, and the linear function which we are searching for. This difference, if you follow that math, must be of this form, because that constant disappeared. You see that constant P of R must be part of this, and that must be part of this, so it disappears, and you're only left with the quadratic, which has X minus R multiplied by something. Remember, this something came from P, and this B1 came from L, and is the difference. So, and that A2 is entirely coming from P. So here we can notice something. Yeah. Here is a pictorial representation of the curve, yeah, representing P of X. And these are different candidate lines. This is one possible line, this is another possible line, this is another possible lines. You see, they all are intersecting the curve at X is equal to R. This must be, this is a requirement. Without that, we are not considering, so we are not considering other lines, yeah, lines not intersecting that point. But of these lines, we want to search for the one that truly captures the direction of this curve. So that will now depend on these two, this coefficient and this coefficient. So let's take some cases. In one case, this coefficient will be non-zero. So when this is non-zero, if you look at this difference, you have X minus R as one factor and X minus R as another factor. If you take that one factor out, yeah, so you will have x minus r taken out, and then you will have something, yeah, and that something will be basically this thing plus that thing and so on, yeah, if you want to write it down. So the point I'm trying to make is that this difference between the two functions will have a single root at x is equal to r, because you can take this factor out only once. You cannot take this factor out, yeah, because you don't have a square there. So, and that is what you see there. The line, when you have a single root between the difference, the line, this line, yeah, this line intersects the curve only at x is equal to r, yeah. So there is only one intersection there. There must have two intersections. We must have two intersections because this is a quadratic polynomial. A quadratic polynomial must have two intersections with a line. The other intersection must be elsewhere. Yeah? Why I am saying this is because when you set x equal to r, yeah, this will be 0, yeah, but the other will not be 0. So this will be 0 only because of this one intersection. So if you look now carefully at these three lines, this line has two intersections. One intersection is here with the curve, one intersection is here. Yeah? So this intersection is at r, that is what we are talking about. Yeah? This factor represents this intersection. Same is the case with this secant line. One intersection there at x is equal to r represented by this factor, and the other intersection is there, which is not at x is equal to r. But this figure also shows these are called secant lines. Any line which intersects a curve at multiple points is a secant line. We also suggest that there must exist a line which we will call the tangent line that intersects the curve at a single point. Now we know any line must intersect it twice, so which means that both those intersections are happening at this point, and we need to see that from algebra. So you must combine algebra with geometry if you want to increase your understanding. Now let's look for the other scenario. So in this case, because the intersection is only once, the slope b1, remember b1 is the slope. b1 is the slope of our line. Yeah, our line had this form: b0 plus b1 x. b1 is the slope. This slope of this line or of this line or of any other line which intersects the curve only once cannot represent the true direction of the curve. So it captures one aspect, yeah, it intersects the line, but it cannot capture the direction aspect. For that, let's investigate the other case where the coefficient is 0. So if this coefficient is 0, this x minus r multiplies 0. So this difference between the polynomial and the linear function is that square of x minus r. And now this term is not bothering us, which means that this x minus r is appearing twice in this expression. Yeah, you have x minus r and x minus r again, and that then multiplies 2. So now x minus r is appearing twice. So the difference has two roots. They are repeated roots. Yeah, you can set x is equal to r twice, and when it has double root or repeated root, we can say that both the intersection of so this case must correspond to the tangent line we were expecting. Yeah. So at this x is equal to r, these two intersections now are collapsed into a single repeated intersection. So this is a special value of b1. b1, according to this equation, if you take this b1 to the other side, must equal this value, a1 plus twice a2r. This slope truly represents the direction of the curve at the point. So what conclusions can we draw? This is exactly what we mean by a line tangent to a curve at a point. What do we mean by a line tangent to a curve at a point? You have used geometry concepts, but we now provide an algebraic explanation for that. What we mean by a tangent to a line to a curve at a point uh, is a line that intersects the curve twice at a point, at the point in question. Now, the repeated intersection is actually the condition which is usually mentioned as a line that just touches it. Now, when you say a line just touches it, it can be informally described by figures, but the precise argument is that any other line will have two intersections. Sorry, that's not true because one of the intersection must be here. So for example, this line has two intersections with the curve, one here at the point in question, one elsewhere. Now, if we have a line which has both intersections at the point in question, that will be just touching it. It's just touching it. Yeah. And lines intersecting a curve at distinct points, they are said to be secant. Yeah. So we are actually disregarding all the secant lines and we are picking the tangent line. Now, the slope of that tangent line, remember, there is no such thing as the slope of a curve. So the slope of the line which is tangent to the curve, that because that truly captures the direction of the curve, and that is exactly what we were looking for, that is what we call the derivative of a function, in this case the polynomial, at a point. So this, what we mean by the derivative of a function at a point, it is the slope, not of the curve, it is the slope of a line, not a line, the line, tangent to the curve at the point of tangency, yeah, not anywhere else. Now we had a function and we chose r. Now there is nothing special about r. No? We could choose any point x. We can choose any point x. We can do the same here, anywhere, every time. Every time we will be looking for lines and we'll pick the tangent line, yeah, repeated intersection. So we can then have a function. Yeah, we have a function that maps each point. So each point I choose, each point. At each point I find a line tangent to the curve and then I find the slope. So if I collect all these slopes, I will have a mapping. I will have each point x and I have to map this to the slope of the tangent at x. Yeah? Not any line but the tangential line. So this I get a new function. That function will be called the derivative function. Remember, don't confuse this with that definition of a derivative. That was the derivative at a point at x is equal to r. Now we want to set it free. So p prime will represent the function which maps each point to an appropriate slope. Another notation is dp. D is the operator, derivative operator. Now this derivative operator is actually a function from the set of all functions, yeah, the set of all functions, yeah, and it gives you a set of other functions, the derivatives. So the point I was trying to make is that there is a difference between the derivative at a point, which is a single slope, and the derivative seen as a function. So when I write p prime of x, this should be seen as the derivative of P at a point, and it must not be confused with the P prime, which is a function. So this is just a value of that function at x. So we can now express our quadratic polynomial. This was our starting point. We know we expressed it in terms of x minus r, so this was the constant. And now we see that this coefficient, yeah, this coefficient turned out to be the derivative at r. If you follow the previous discussion, that special value a1 plus twice a2r, this was already there. This was exactly what was multiplying x minus r. So we now expand our function as a constant plus something multiplying x minus r. That something is the derivative at r, and the rest is just a nonlinear term. So the term which does not include any square of that difference, this is actually exactly what we meant by L of x. So essentially what I have tried to achieve by all this reasoning is that I have been able to decompose this given polynomial function into two parts, into a part that is linear, yeah, that can be represented by a straight line, and a part that is purely nonlinear. Yeah, this had both linear and nonlinear paths. I have separated those two parts. So if I set x minus r to delta r to see this as a change in r, I can write this in this form. Then x will be r plus delta r. Take this r to the other side. And now you can see that, okay, if I start with any point r and if I make a change delta r this way or this way, I can see how the function changes when I go from r to r plus delta r. Now again, there is nothing special about r. We could have chosen any point x, so I can replace r with x, and I can replace this delta r with delta x. Yeah, and then I can now write my function as p of x plus delta x, so x and then x plus delta x. Remember, delta can be anything, delta x. And again, I have two parts to this new value. So a linear part, which is dictated by that linear function, and a nonlinear part. Remember, this one is predicted by the linear. So this is the prediction of at the new point by the polynomial, and this is the prediction by the linear function. Now we need to distinguish between two different changes. This is the actual change as you go from x to x plus delta x, and this is the change captured by the linear function, because this is an approximation, and that actually turns out to be the derivative times delta x. Yeah, so if I look there, if this is my function, this is x, this is x plus delta x. So there are two changes. One is the change as I go from this point to that point. So this is delta x, and that will be delta y. Yeah, this is delta y basically. But this is not delta y. This is not the actual, this, because I chose 2 points along the actual p of x. Yeah. So this was p of x and this was p of x plus delta x. This is L of x. So if I go for that tangent line, that tangent line will have a different slope. It will not go there, it will end up somewhere there. So this is what we mean there. So it's customary to write this as dy. So we need to distinguish between this change, the actual change, and the linear change. We can call this the linear change, dy and delta y. So here I define this as delta y, the actual change, and I define this as dy. So d just reminds me that I am only capturing the linear change, not the total change, the change captured by the tangent line, yeah? dy. So this is dy. And that turns out to be the derivative at that point times delta x. Now here we need to distinguish between x and y. Only y is the dependent variable. So you remember it was our choice to call it delta x. We just called it delta x. Now this was our choice. We can call it dx. Nobody can stop us from doing that. I can call it anything else. I can call it h, for example. That was our choice, but this is not our choice. This delta y and this dy are different. This delta y is the total change. This dy is the change captured by the tangent line. So to be consistent, I can replace this delta x with dx because that's my choice. So that I rewrite those two definitions there. I just rename it as dx because that doesn't matter. For independent variable x, it doesn't matter. The difference only is important for y. So there, if I call this dx, so the actual difference will be delta y, and the difference captured by the linear function or the tangent line is dy. And now I can do something cool. If I divide both these differences by the same dx, yeah, so the change along the independent axis, I called it dx. Remember, this dx can be small, this can be large, it's up to me. I don't care how large or how small this is. So that small is actually, I don't care whether this is small or large. It can be any change. So the ratio of the actual change by this dx, which was my choice, this will be the slope of the secant. We know secant took me from one point to the next point following the actual curve. Yeah? So this is delta y and this is dx. And remember, for me dx is the same as delta x. So delta y over delta x or delta y over dx is the slope of the secant. But this one, dy over dx, dy is the change captured by the linear function. Dx is so you see that was the linear function. This will be dy. This slope will directly give me the derivative of the curve of the function, which is actually the slope of the tangent. So that's the punchline. The derivative is the slope of the line tangent to the curve at that point, and I have established that when we write dy over dx, there is nothing wrong. It is perfectly valid. Dy is the change captured by the linear function. Dx is the change we chose along the x-axis, and this change is called the differential. Yeah, differential is not this change. This is just, you can call it the increment. Yeah. So increment is the change, the actual change in the function, and differential is not the actual change. It is the change captured by the straight line approximating your curve. I hope that helps clear those confusions. In the follow-up to this lecture, I will try to explain because I never used limits here. Yeah? I avoided limits. I did not care how large this dx can be. It's my choice. But there will be functions for which it will not be so straightforward. There we will require limits, and we will have to be careful about this dx to be small. How small, that has to be made precise. But this initial lecture was important so that you get the big picture. The big picture is that derivative is not the slope, because the slope is a property of a line, not a property of a curve. And what we mean by the derivative of a function at a point is the slope of the line, not a line, the line tangent to the curve at that point. And if we do that procedure at every point, then we see a function mapping each point to an appropriate slope, and that function is then called the derivative function. So bye for now.